Here's a recap of the chain rule investigation we did. The idea of the chain rule is always that we have some situation, let me insert this in here, where we have some initial variable in this investigation that started with time, and then there is a function of that, in this case it's the position s, and then there's a function of that intermediate variable, in this case it was the temperature. So we've got an initial variable that leads to some intermediate variable, and then that leads to some final output quantity. And we are given, usually the situation is we know how these two variables relate, how the intermediate depends on the initial. So that is position versus time, things like velocity. And we also know how the final depends on the intermediate. That, in this case, it was some information about how the temperature varied as we move along the rod. But what we really want is to relate the initial and the final, and to kind of drop the intermediate and shortcut this procedure. Have an arrow all the way from initial to final. So, going quickly through the first parts, because I don't think people have as much trouble with that. If we know the velocity of the bug at time t equals 1 is 5 meters per second, then we can just say that how far does the bug go? Now, this is one thing that is really important, is that's a verbal expression, but we actually have a notation for that. It's called ds. About how far does the bug go? It's called ds. And it is, of course, ds dt times dt. And we know those two pieces of data. That's 5 meters per second times 0.01 seconds. And so that's 0.05 meters. Being inconsistent about math mode, but whatever. Okay. So, we know how far the bug went. Now, suppose we also know how sensitive the temperature is to a change in position there. So this is something that doesn't know about the bug at all. It just says if I just change from one thermometer to a nearby thermometer, it gives me an idea of how much the temperature changes. And we're just going to investigate that separately. So we're really just looking at T, big T, the temperature, and the position right now. And we're only going to put them together in part 3. Okay. So if I look at one thermometer in this region near s equals 7, where this data is given, to another one which is 1.1 meter, let's say away from it in the positive direction. I forgot to put that in there to be definite. Okay. Then by how much does the temperature change? Oh, we've got a notation for that. That's d big T. That's equal to how sensitive is the temperature to a change in position. A derivative is often a sensitivity value times ds, and we just said what that was. Okay, so it's going to be minus 2 times 0.1, which is going to be minus 0.2 degrees Celsius. Okay, so what if I move a different amount? And of course, the great thing about this idea of differentials is it just answers those questions very easily. It's the same exact equation. I just put in a different amount of motion, and I get a smaller temperature change. So these were just artificially put in temperature or motion. But now, what if I put in a completely variable amount, ds? And that's going to be in preparation for putting in the ds that's appropriate to the motion of the bug. So I'm just going to get I'm just going to put ds here, and that's going to be it. It's going to be minus 2 ds. And if I wanted to be careful about it, which I probably should, it's minus 2 degrees Celsius per meter times ds, and then the ds is going to come in with a meters, and that's going to cancel it out and give me a degree Celsius. So this is one of the key things that we're going to use. So now, number 3. What we're trying to figure out is we have the clock at t equals 1. The bug is going to move a little bit, and we're just going to let the clock run for a small, fixed, simple amount so we can start thinking about derivatives, 0.01 seconds. And we're going to want to figure out how fast is the temperature changing. So one way to do that is let the clock run for this small amount and try to predict d big T. Okay. So it's really just filling in a few blanks. d little t is 0.01 seconds. If we're going to predict how much the temperature changes, then the reason the temperature is changing is the bug's going along the rod, and the rod is changing, the temperature of the rod varies with position. So we need to figure out how far the bug went. That was number 1. And now we can use number 2 which said, oh, if you tell me an arbitrary distance that I move from one thermometer to another along the rod, I can tell you what dt is going to be. dt, I just plug that in, it's going to be minus 2 times 0.05, which is minus 0.1, and that's going to come out in degrees Celsius. Oops, degrees Celsius. So this is really, we've really accomplished the main thing right here. We inputted the initial value, the initial change in the initial quantity, and in 2 stages we found the change in the final quantity. And now we're just going to take the ratio. That's going to be minus 0.1 degrees Celsius over 0.01 seconds. And if we divide that out, we get minus 10 degrees Celsius per second. That's the rate of change. That's how fast the bug's temperature is changing. That's pretty fast. That's a pretty drastic change, but it's reasonable. It's possible. So every second the clock ticks, we're going to predict that the bug's temperature goes down by 10 degrees per second. Now, I probably should have switched 4 and 5 here. Let's look at number 5. And let's just look at the numbers we have. We have the dt ds, that was one of the givens. That was minus 2 degrees Celsius per meter. We had that ds dt, that was another one of the givens. That was 5 meters per second. Give a little space there. And we just figure out that d big T by d little t. What we were really interested in, the final quantity differentiated with respect to the initial quantity, was minus 10. Well, hopefully the guess is pretty obvious here as to how it looks like these things are coming together. It looks like they're multiplying. And indeed, that's the chain rule. Whoops. It tells us that these quantities are just related by a product. And let's see if that makes sense. Why would they be related by a product? Why, is this just an accident? Well, what happened when we took this 0.01, what did we do to get the ds? We multiplied by 5. To get the big dt, we multiplied by minus 2. We just took this 0.01 and we just multiplied by 5 and by minus 2. That amounts to multiplying by minus 10. And so that's really the simple thing that's going on here. Oops, not equals, times. So the nice thing is that this looks just like we had fractions. And that's exactly how it worked out. We actually looked at these differentials, and it works out just like they have fractions. To make this more rigorous, you have to do the limits and all that kind of stuff, because when you do differentials, you're really hiding a lot of approximation processes. But really, as long as we trust that those approximations are going to get better and better as all the dt's and ds's get smaller, then this really is a pretty secure fact. Okay. Now, one subtlety from number 4, if the thermometers were in the wrong place, remember, one of the things that most people go right by here is that we happen to know that the bug's position at time t equals 1, which is when we're actually taking this derivative, when we care about the rate of change, he's at 7. And it says luckily we've attached some thermometers right around that point at s equals 7, not s equals 1, which wouldn't make any sense. It's t that's equal to 1. The clock reads 1 second. The position happens to be 7 meters. There's no reason in a random example why the 7 and the 1 would be the same. And it's really crucial that the thermometers had to be at the right position, at s equals 7, or in other words, at g of 1. So this is really f prime of g of 1, which was the crucial data. That's why I asked number 4. Suppose somebody had mistakenly said, oh, I want to know f prime of 1. That's not going to help us, because that's not where the bug is. The bug's at s equals 7. Just because t equals 1 doesn't mean s equals 1. Okay, so this would be useless. That helps in this last bit when we look at the functional form of this equation. Okay, here big F is the composition of the two functions. It's the shortcut going all the way in one step from little t to big T. Okay, so this is supposed to be the output of this is supposed to be the temperature. And the intermediate stage, S, is the output of just G of t. So let's see, the derivative of the whole thing, that should be dt dt. Okay, so this left-hand side should be what we just found, the temperature with respect to time. Well, what did we find? ds dt, that's the derivative of the function that gives us position as a function of time. So that should be g prime. Okay. Now what is dt by ds? That was the derivative of the function that relates big T to little s. If you look back in the sheet, that's f. So that should be an f prime. But why don't I just have a t here? Well, that's exactly what I was just talking about with the position of the thermometers. It wouldn't make sense to put a time value here, because little f is supposed to be a function that takes position values and gives you temperature values. Instead, you need g of t there. So you look at what the clock setting is, you find out where the bug is, you then look at how sensitive the thermometers are to a change in position at that position, and then you multiply that sensitivity by how fast the bug is actually moving. So that's worth writing down in itself. It's the sensitivity of temperature to a change in position. That's a big long-winded way to say this dTds, or f prime of g of t, and I'll say at the correct position. I know these are being annoying, but oh well. Okay. And then times the actual velocity of the bug. If the bug weren't moving, he wouldn't be changing temperature at all. And if the rod didn't have any sensitivity of temperature to a change of position, again, it wouldn't be changing temperature at all. It's both of these contributing together.